Okay, so here's our first example of a weird inner product. We're dealing with the polynomial space P1, so that's linear polynomials. And the way we're dot producting these vectors, these polynomials, is by multiplying them and integrating it over 0 to 1. So let's just take an example here. Let's take the dot product of x plus 2 with 3x minus 1. Let's figure out what this dot product is. So this is the integral then of 0 to 1 of x plus 2 times 3x minus 1. And then we multiply this out here, 3x squared plus 5x minus 2. And then we integrate this, is going to be x cubed plus 5 halves x squared minus 2x from 0 to 1. And we should get 3 halves. So this is showing you a different way of taking a dot product here. Of course, right now I'd like us to prove that this function satisfies the 4 conditions to be a dot product. So the first condition is the commutative property here. So if I do f of x inner product with g of x, that's the integral 0 to 1 f of x times g of x, which, because f of x and g of x are functions where the answers are just regular numbers, and if you multiply numbers together, it doesn't matter the order you write them in. So what that means then is that f of x times g of x is the same as g of x times f of x, which is the same as g of x inner product f of x. So that's property 1 done. All right, so let's look at property 2 now. Property 2 said that if you are adding 2 vectors in the second component, you can break it apart. Well, let's go ahead and see here. We know that you can distributive here, distributive property. And then we know by properties of integrals that you can in fact break this up into 2 separate integrals when you're adding inside. And that's the same as f of x inner product with g of x plus f of x inner product with h of x. So it does satisfy condition 2. Now condition 3 is when we have a constant here. And we're going to turn this into an integral now. Integral 0 to 1, c f of x, g of x. And we know integrals, you can always pull out constants. One of those things you learned in calc class. And we get c times the inner product of fx times g of x. So you're able to pull out c from the function. So again, all these are just showing that the properties hold, that this is actually going to be an inner product. There's one more to do, and that is property 4. This one can be the trickiest. It's when you inner product something with itself, you need to make sure that this is always going to be non-negative. So notice here f(x) times f of x is f of x squared. And then there was a property that you may have forgotten from calculus class that said if the thing you're integrating is always above the x-axis, then the integral is guaranteed to be greater than or equal to 0. And so since if you square a number that's positive, integral of something positive is positive, so we're good there. And the only time that this integral is going to equal to 0 is if the function itself is always 0. So that means condition 4 is satisfied, and we have this example. Now with that said, I likely won't ask you to prove that something is an inner product. More likely I will give you a function and tell you it's an inner product and ask you to find dot products and things along with that. But it's good to at least see this one time here, see how things go.